Good evening and welcome to this IPA colloquium. We are very happy to bring a young, bright woman researcher today to you. And I would like to say she's your own very own scientist. This is Seema's alma mater. I believe her college also is joining here. So we are extremely happy to have her give this talk and tell her here. It's really the effort of IPA to nurture the young talent, and here we have a your own role model for you coming from you amongst yourselves. So Dr. Seema Sharma will give today's IPA colloquium, and before that I just want to take a moment to tell you briefly about IPA. So let me just share my screen. Yeah, I hope you can see my screen. Yeah. So IPA, the Indian Physics Association, many of you may be aware about it, was founded in 1970, almost 5 decades back, and with a goal to actually bring together the physics community in the country, and particularly the younger generation, to help them understand some nuances about research, get introduction to it, and learn about the latest development and the excitement in the field. IPA has more than 40 chapters distributed all over the country, as you can see here. And IPA holds a series of lectures as well as brings out bulletins. One of the main bulletin which is regularly brought out is the quarterly bulletin Physics News, which is shown here and is also available online. So please visit our webpage for more information on the IPA programs, links to various IPA events. In the last 2 years after the pandemic, since the events have been online, many of the lectures are available in the YouTube, and you can avail of this to acquaint yourself with different fields. So the IPA also gives the awards biennially for both for senior scientists and young scientists, recognizing their accomplishments and contributions to the field. In addition, it liaises with the other national academies of India, other societies, and the international societies like American Physical Society, Institute of Physics, UK, and is a member of Association of Asia Pacific Physical Societies. The current office bearers of IPA are Professor Ramakrishnan, Director TIFR, who's the President, Professor Tanushree Das Gupta, Director SN Bose Center, who's Vice President, myself, Vandana Nanal from TIFR, General Secretary, Professor Samit Mandal from Delhi University, Joint Secretary, Dr. Aradhana Srivastava from BRC is Treasurer, and IPA, in a unique effort, actually established a Gender in Physics Working Group in 2017 to address the pressing question of gender paucity or gender inequity in the physics community, particularly in Indian context. And current chair of that group is Professor Shubhabati Goswami. And, last year, after the IPA had a webinar series to celebrate 5 decades of IPA, and given the successful response it had, we continued the series with the IPA monthly Colloquia series. So we have the IPA colloquium on the first Saturday of the month. If the first Saturday happens to be a major holiday, we go to the second Saturday, and a variety of speakers have been giving the talk, right from the subjects like from the Nobel Prize in Physics in 2021 to various innovative technology and applications. And the last colloquium was given by Professor Poonam Chandra on astronomy, and we are actually happy that both Poonam and Seema we have in February and March, which is kind of coincident with the both International Women and Girls Day in Science in February 11, and now the International Women Day in Science. And today Seema will take us to a completely different dimension, from the astronomy to the very tiny interiors of the particles with accelerators. So I now stop here, and before I stop, I should thank the University of Rajasthan for hosting this talk very readily, and all the people, all the students who have joined from the university and the nearby colleges for this, both on the Zoom and YouTube. Thank you very much. So over to Dr. Rashmi.
Professor Sharma hails from a small town in Rajasthan called Rajsamand. She got her bachelor's degree from Maharani's College of the University of Rajasthan, where she was a physics honors student, and I've had the proud privilege of teaching her. Her master's was also from the physics department of the University of Rajasthan. And thereafter, she moved to PIFR for her PhD with Professor Sunanda Banerjee, working in the CMS experiment. After that, she was the postdoctoral research associate at the FNAL, Fermi National Accelerator Laboratory, working once again in the CMS experiment at CERN in Geneva. During her participation in CMS, she has served as the convener of Supersymmetry Physics Group, as well as Jet and Missing Energy Group. She is also currently the deputy spokesperson of the Indian participation in the CMS collaboration. Her research interests are around new physics searches and calorimeter detectors. Presently, she's very involved in high granularity calorimeters for high luminosity Large Hadron Collider. She's at the moment serving as the professor in the physics department in IISER Pune. During her career, she has had multiple fellowships and awards, and the most prestigious one being the CMS LHC Physics Center Distinguished Researcher, both junior as well as senior researcher, and TIFR Alumni Association Scholarship for Career Development, which is supported by the TIFR Endowment Fund. She has given multiple invited talks at various places, and the most coveted one being the one at the CERN theater, where I don't remember the title here, but that was the one that I had we are very proud that she, from our university, has given that particular talk. So I will get out of the way after so much of delay, and will let Seema take over. Please, Seema.
Thank you, Rashmi ma'am and Vandana, for the nice, kind introduction. So I think I can't be very formal here, but I mean, this is really nice to get back, and I can see myself sitting among these students, and Rashmi ma'am is still teaching me. I mean, my introduction to high energy physics was actually by her, and I see Sudhir Ranewala sir also connected, and he is the one who taught me in Maharani's College. Actually, Rashmi ma'am taught me in first year and Sudhir sir in second year of BSc. And after that, I somehow had always the interaction with Sudhir sir, but he never taught me beyond that. But I was always in touch with them via CERN and at various places. So since I said that, okay, fine, it has been like very sort of ups and downs and mixture of the experiences. So since I see a lot of youngsters connected, this one point which I would like to say is that there is like sort of nothing like role models which exist in books or in the television screen. You have to find out just nearby you. And most important is you have to find out support structure for yourself. Okay, and what Rashmi just told about this the talk at CERN auditorium. So luckily Sudhir sir was there in the audience, and I could see once I finished my talk, the emotions flowing out of his face. And then you realize that your mentors have much more dreams for you than you can think for yourself. So probably I never thought of like giving a talk at CERN. Okay, and I think it was more a dream coming true for him rather than for myself. So it has been really a sort of, I think I have been very lucky with my teachers and mentors at every stage of my career and my life. Be it the school, be it college, be it later, everywhere. So please figure out support structure for yourself. Don't assume the things. I mean, if you want to do science, you can't assume anyways, right? So don't assume, okay, fine, this is our society, this is the complication, you have to figure it out, and it works. But find out support for yourself, and that's close by, that's nearby. So after this, I think, as I said, that is sort of also a personal moment for me to get back to all of you. So let's get started. Let me share my screen. Okay. Can you please confirm it's full screen?
Yes, it is.
Perfect. And I mean, if I go fast, I have tendency to speak fast. So please stop me wherever you think that I'm going very fast. I have tried to keep it at the introductory level, but at some places it might get complicated or I might not express myself well. So please point out. I will always be happy to come back if there is any aspect of my work which you would like to know more about, so that we can sort of try to get back with more details. So today I will give you more of an overview what the CMS experiment is about and how we sort of connect to the bigger picture of the our studies and what we are trying to do. So the title of my talk is the CMS experiment and missing momentum microscope. It's sort of a microscope in the sense that we are trying to really probe the very small structures, but I specifically mentioned missing momentum, and you will understand that why I said so. So let's get started. So why are we doing the particle physics and the research all about? So what we are trying to understand is that what are the fundamental constituents of our universe, and how do these constituents talk to each other? So basically how the interactions happen. Now, when we say universe around us, what do we mean by? Because then the bigger structure comes, okay, fine, when I open up my eyes and see the sky, what is going on? So what does the universe comes in picture, and where the fundamental constituents, how they connect to each other? So this is more of a generic picture. As you can see that as we grow up, we always like familiar with what we see from our eyes, that is the whatever the optical structures. And then we talk about like all these planetary structures, then we read about the galaxies, astronomy, and the really microscopic picture comes only later. Okay, so then we talk about, fine, first time we see in our school that, okay, fine, there are cellular structures, and I don't know how many of you actually saw in microscope. My first experience was the onion peel when I was in class 6th or 7th. And that was super exciting. I mean, just to be able to see, but there also we were still using the optical range, optical wavelengths. So then you go down further, and then we have the atomic structures and the subnuclear structures. And that's what our focus of the talk today will be. I don't know if you people can see my cursor also. I don't think so. That's okay.
No, maybe you can use the laser pointer.
No
you
cursor.
To that.
Yeah, I think once I put in the full screen, I just can't use the mouse.
Okay.
So that's fine. So when we talk about, I think the smaller structures, and we are getting away from the visible light, what we are making use practically of the fact that the matter, the subatomic matter also exhibit wave properties. It's not only the particle properties, and this is something which we are all familiar by now. And the idea is that if you use a larger wavelength, you see basically a blob here and no internal structure. Once I put in the full screen, I just can't use the mouse.
Okay.
So that's fine. There is some echo, I think. I heard myself. So probably YouTube transmission delays. That's okay. So once we use the smaller wavelengths, this basically more energetic particle, we can use these particles as the probe. And that's what we are familiar with the electron microscopy and all that. So larger the momentum or the energy of the particle is, the smaller is the wavelength, and we can really resolve the smaller distances and try to sort of understand this better. So this is one of the fantastic tools given to us by G. Broglie, who gave us this understanding that actually this is more or less that why Rutherford ended up using the radioactivity to study the nuclear substructure, the atomic structure further, right? I mean, he had to wait that, okay, fine, he can have the alpha particles until he can see there is something more going on inside the atom. So actually, that's a fun problem to solve and get the numbers out, that you can really use the alpha particles coming out to see the nucleus structure. So the mundane matter around us is essentially boils down to the atoms, and we know the atom has an internal structure. Most of the space is empty. It's electrons, and the inside is the nucleus where most of the mass is. And the nucleus also consists of the protons or neutrons, which are further composed of the quarks. So this is more or less our story so far, that we are made up of the quarks, which are up and down types, and the electrons. And we know about the neutrinos, which has been inferred from the study of the radioactivity. So this was all okay and feels like, okay, fine, why do we care? I mean, the point is here is that this much, like if you really see the atoms, those are the smallest entities which retain their chemical identity, right? So Mendeleev's table came up like a century and a half ago. So why do we care beyond all this? So the most recent understanding we have is that where we all came from, where did it all come from, the universe we see around, whether it's microscopic, macroscopic, we are talking about is the Big Bang theory. That is the sort of most accepted hypothesis so far. that something happened at the beginning of the universe where the temperatures were way too high and the distances were like very compact. And then it started cooling down and expanding. And where we are today, that is the most right side of the slide I'm showing here. And then you can go back and try to see how the structures developed, how all the cosmological microwave background and all these things came in picture. But at the beginning, it was all about these elementary particles that we are trying to understand. So what Vandana said before, that the previous talk was on the astronomical structures and all, what we are trying to go is a little bit back in time. Okay, and that's where what we and why do we care for all these things, that okay, why our mundane matter doesn't explain everything, is because there are observations which cannot be explained by just looking at what we already know about the atoms and the up to the quarks or neutrinos. So these are all the sort of cosmological measurements or astro measurements. The first one shows the galaxy rotation curves. So here the idea is that you look at the velocity of the stars or the particles as you are moving away from the center of the galaxy. And what we would expect from our normal, from the understanding of the gravity or the Kepler's laws, that the velocity should decrease. That's what happened in the planetary systems, for example. But what comes out, there is a huge discrepancy with respect to what is expected and what is observed. Okay, observed is more or less flat. So this essentially tells you the how the matter is distributed there, but that matter is something which we can't see. Okay, and that's what we call the dark matter. So that's one possible explanation, that there is a halo around in the galaxies, which is not visible to us, but there is something going on. There are some other measurements, for example, gravitational lensing. So this is one picture from Hubble telescope where they get sort of an impression of a galaxy too far away, which is hidden by the cluster which is being seen here. But you can still see these arcs around, and that's sort of coming out as a lens effect. And there's something more going on, and the light is bending. So this light is bending is one of the like key features, which is like sort of success of the last century. So what is happening here is that when all these things are put together and all the measurements are done, it comes out like something 25% of this matter is the dark matter, of the universe is dark matter. So then now the question we want to ask is it a fundamental particle? What is its nature and identity? Okay, so moving on, that is our sort of quest for fundamental particles. And a lot has been going on in the last century. We learned a lot. And what we have established is the standard model of particle physics. Is basically the standard model of elementary particles. What we have identified so far is the particle content and the interactions established in the last few decades. So you see here the particle content. There are 3 generations of the quarks, which I show in the purple, these particles, which is the up, down, charm, strange, and top, bottom. Then there are 3 generations of the leptons, the electron, muon, and taus, and their counterparts, the neutrinos. These 3 generations are identical mostly, except their masses. So if you write down their theory, if you don't put in mass, they are all sort of interactions are similar. These, the way we understand these particles interact with each other is via the exchange of the force carriers. This is what the gauge bosons. These are the spin 1 particles. So far we know of the 4 interactions, the strong interaction, electromagnetic interaction, and weak interaction, and the gravity, which is all around us, but that is not incorporated at the elementary particle level yet. So the standard model takes care of these 3 forces. And the force carriers, I mean, we know by now the photons is for the electromagnetic interactions, gluons for the strong interactions, W and Z for the electroweak interactions. So the way we understand that how these particles acquire their masses is via the Higgs boson. And then we can write down completely a mathematical theory, which I'm not getting into the details, but showing you as this cup from the Sun souvenir shop. And this really explains us what the particle interactions will be and what their rates will be, and we can really measure them experimentally. So the discovery of the Higgs boson in 2012 actually completed the particle content of the standard model. But the standard model doesn't explain the dark matter. We have no idea what is going on there. Neutrinos are not sufficient to explain the quantity of the dark matter observed or reported. Then why there is more matter around? Where is the antimatter gone? Because at the beginning, everything is supposed to be symmetric. Why there are 3 generations, masses of the neutrinos, quantum nature of gravity. So there are many such fundamental questions which we don't know yet. So we know a lot, but there is a lot which we don't know. So moving ahead. So what could be the dark matter particles? So the most popular hypothesis is the weakly interacting massive particles. Why I say weakly interacting? Because they really don't interact with the matter which is visible to us. Okay, same like neutrinos. You must have heard about the neutrino experiments, how difficult they are and how big detectors we need. So the properties are essentially, there is no electric charge because it's not luminous. There is no strong interaction. They interact via weak and the gravitational interactions, or maybe some weaker force if there is a new force which exists. They are stable, very, very long lifetimes. And they can be a very wide mass range. So how it can happen? I mean, what can be a general understanding? The point here, the picture which I show here at the bottom, where I say the two dark matter candidates and the two SM particles. So what can happen is that the two standard model particles, they can interact and they can give you two dark matter candidates, or it is called the production of the dark matter, which is going from right to left. And if the two dark matter particles can interact and they can convert to the standard model particles, that's what we call the annihilation. Okay, so what the current hypothesis is that in the very early and the hot stage of the universe, the dark matter production and the annihilation was equal. So there was some sort of a thermal equilibrium there. As the universe cooled down and expanded, the dark matter production decreased because you don't have now enough energy to produce these particles from the standard model particles. And so the number density also decreased. Now, as it expanded further and further, the expansion took over. So now the dark matter particles also cannot find each other to annihilate. So what is the net result? There is a fast expansion of the universe. The dark matter cannot annihilate further. There is a net non-zero dark matter content in the universe. That is the basic idea. Okay, the picture I show here, this graph and all, let's not get into detail, but the basic idea, the three colors which I show here, the red one, purple one, and the blue one are essentially referring to these 3 points. That where the stage we are, that universe has expanded so much and cooled down so much that there is a net non-zero density of the dark matter content in the universe. Okay. So let's move ahead. And how do we go about searches? So this is what happens. Again, my central picture here is the standard model particles which can convert to dark matter, or the dark matter particle existing around in the universe can interact with the detectors. So there are 3 ways to do it. First is the indirect detection. So the first 3 pictures I show here from the satellite-based experiments or like the telescopes is essentially saying that, okay, there may be some sort of antimatter density which may observe. So this is the way indirectly we check it. Right now we know that there is more matter, depending upon what we understand so far. If there is any excess in the antimatter, we can sort of try to gauge it that, okay, something happened or something going on somewhere in the corner of the universe. Or it can be the direct dark matter detectors, which is essentially this right side, which I show on my slides. There's some of the examples like the Super CDMS, which is the direct dark matter detection, or it can be the Xenon 100. These are really underground experiments and very, very like a large detector volume, because the dark matter doesn't interact very quickly. The rate is very, very small. So if they can see 1 event per day, which can be a neutrino most of the time. So these are the what we call that dark matter passed through the detector, it interacted and left its signature. Other way is that we make the standard model particles sort of talk to each other and create the dark matter candidates, and that's what we do at the LHC. So can we produce the dark matter at the LHC? So that's what the topic of the talk today will be. But dark matter directly existing, there are several other theories which also predict the dark matter candidates. So supersymmetry is one of them. So for example, why the fermions and bosons, why they have to be so different? There can be that there is an higher level symmetry, which is like makes them, put them on the same footing. So for every standard model particle, there is a supersymmetric particle differing by some spin half. So my every spin half particle, the quarks and neutrino leptons, they will have a supersymmetric counterpart. And similarly for the bosons, there will be a fermionic counterpart. And this also, if the lightest supersymmetric particle is weakly interacting and electrically neutral, then it is a viable candidate for dark matter. This is one of the reasons that supersymmetry has been like quite sort of popular. Now it's a broken symmetry. So far, we have not seen any spin zero counterpart of the electrons. Okay, so probably these particles are very, very massive and as compared to their standard model cousins. And that's exactly what we want to search for in this LHC. Now, when I talk about this dark matter candidates, there need not be only one kind of dark matter candidates. There can be multiple particles which can contribute to the observations, the observed phenomena in the universe. Now, there are several other reasons that supersymmetry is very attractive. This is that when we learned about like the Higgs boson and the electroweak symmetry breaking, that time it came out that the theoretically their mass is unstable. So there are very large corrections to the Higgs boson mass. If you have the supersymmetric particles, then the Higgs boson mass it theoretically gets stabilized. Experimentally, we know it. It's 125 GeV close to that. And it cannot be like standard model is completely right and wrong at the same time. So maybe something more going on. Then it provides a viable dark matter candidate. It also provides scenarios where the coupling of the 3 interactions, the weak, electroweak, and the strong, they also try to become unified at some higher energy scale if you incorporate the supersymmetry. But you have to be careful here. The reason I picked up this example is that whatever new physics we ask for, it has to be consistent with the standard model. Whatever measurements we have made so far, it cannot go and break it down. So it cannot happen that suddenly my proton start decaying. We know that it doesn't decay so far. Okay, so whatever new theories we are talking about, the predictions have to match with the standard model measurements. What we have so far, it can be extension to that, what has not been measured so far. Okay. So how do we create these particles? Because I said that all these particles, the dark matter particles or supersymmetry particles, they are very massive. So how do we go about and create these particles in the lab? Now, again, Einstein gave us very nice understanding to this one, that we make use of the mass energy. So we accelerate the electrons and protons to very high energies and collide them. So basically make them talk to each other. And at the Large Hadron Collider, at present, we are accelerating the protons to 6.5 TeV, and we are colliding at the center of mass energy of 13 TeV. Now, I'm using this energy, the unit TeV. I mean, you can think of that the 1 GeV is approximately the mass of the proton. So that is the unit we are using in our. And I will come back to a few more masses in coming slides. So what we are doing at the LHC, it's a 27-kilometer ring, and it's 100 meters underground at the borders of the Switzerland and France. When we are colliding these protons at such high energies, we are actually squeezing this energy into a space which is very, very small. I mean, I write here the example of million times smaller than a mosquito size, and the temperatures which are billion times higher than the sun. So what we are doing at that very moment, we are actually creating sort of the conditions which are similar to the Big Bang, and we can try to create more fundamental particles there. So that is like what we are trying to do, have the energy density and temperature at that particular point. So this is, I think, sort of a cartoon which shows here that every 25 nanosecond, we have such one mini Big Bang created. Now, out of these, not everything is at the high energy we need to produce our particles, but some of them are. Okay. So what is happening at the proton-proton collisions if I put in a nutshell? So the protons, we know that they are not fundamental particles, they have internal structure, and we know that they have 3 quarks. But that is not completely complete picture of it. It has much more going on at these high energies. It has a lot of gluons and the quarks-antiquark pairs, which are the quantum fluctuations. So at the LHC energies, we are referring to the interactions among these pair of quarks and gluons. Okay, so that's what we call the partons. Now, why? I mean, the interesting thing about the hadronic colliders that they are really discovery machines, because we can really scan a lot of energies there. It's not a fixed energy like an electron-positron collider. Okay, because we don't know what when the 2 quarks and the 1 quark and gluon are colliding, it can be any standard of the center of mass energy depending upon what is allowed by the parton distribution functions. So that is the fraction of momenta carried by these particles. So that makes it all the more interesting that why the hadron machines are the discovery machines. If you want to go for precision measurements, you have to go to the electron-positron colliders. The muon colliders will be much better, but that's right now a dream. So as these particles are interacting, it can be most of the times it's the strong interaction because that dominates the interaction strength. But sometimes we can produce the dark matter or the supersymmetry or the top quarks or the Higgs bosons. So the challenge is, how do we identify this handful of collisions? Because maybe there is one SUSY event produced in like 10 billion collisions. Okay, so that's what our challenge next is. And we will just go through that, how we do that. So before that, the question is, how do we study these particles? And that's where the particle detection techniques come in picture. So here again, I show again the particles we are talking about, these standard model particles or any new physics particles. But most of these massive particles decay. And the detectors can see only the particles which are stable. Stable here in the sense of the scale of the detector. So basically, it should be able to reach that 1 millimeter distance or few millimeter distance and interact with the detector. If it decays before that, we will see only decay products. So what I show here in this table is essentially the lifetime, which shows in the last column. And you can see that most of the particles, they have like the lifetimes of 10 to the minus 13, minus 17, minus 25. And there is no way that they will reach it to the detector. Even if you have large momentum of these particles, that means the large Lorentz boost. Okay, so only particles we end up seeing are essentially the muons in the detector, which is the lifetime 10 to the minus 6. So if it is very high momentum, it will make it. I mean, we see all the cosmic muons reaching the Earth before decaying, right? It's the same phenomena you can think of. And then is the neutrons and the pi plus pi minus, the charged pions, which is the lifetime of 10 to the minus 8. Even the pi zeros, decays by electromagnetic interactions, and the lifetime is very small. So it immediately goes to the 2 photons. So, and the other point is the quarks and gluons. We don't see them there, quarks and gluons. There are no free quarks and gluons. They immediately convert to a shower of particles. That's why I show in the bottom, this picture here on the bottom left. And the particles which are coming out there are essentially hadrons. Most of them are charged pions and the neutral pions, and there are some kaons and the proton neutrons. So in order to detect, the particle has to interact with the detector and deposits its energy. That's the first point. At the end, what is happening, whatever the particle energy and mass is, ultimately the interaction of these particles, the charged particles mainly, is finally converted to an electronic signal. Okay, and the neutron and photon also creates the shower of particles. That's what I come to in my next slide. But ultimately, we are talking about an electronic signature that we have to see. Even if it converts to a scintillation light, ultimately to record it, we have to convert it to an electronic signal. The neutrinos in dark matter do not leave a visible signature in the detectors. As I said, that their interaction rates are very small and they just fly through the detectors. So we have to figure out how to detect them. So what we do in generic high energy collider detectors. So what you have to keep in mind that each of these particles have their way of interacting, and not a single technique will work for all. It's simple that the simplest example is our eyes, but that is tuned to only the optical lights, optical range. Right? All other electromagnetic spectrum, we know they exist, but we can't see with our eyes, right? The same thing goes in here. So we have specific detectors there. So in general, whatever collider detectors you see, the first one is always a tracking chamber, which is also within a magnetic field. You want to have minimum deviation to the path of the particle. So you don't want to sort of distract it at all. So that's where we measure the momentum of the charged particle. So you can see here, what I'm writing is the photons, electron, positron, muons, charged particles, the pi plus, pi minus, and the protons and the neutrons. In the first one, we are measuring the tracks or the momentum of the particle, and there the neutral particles don't deposit any signature. Then comes the electromagnetic calorimeter, and that's where the electromagnetic showers are created. So these are the particles like the electrons, photons, and the electron, positron, and the photons, and the pi zeros, which have converted to the photons. As I said, the lifetime is quite small. And then comes the Hadron Calorimeter, because their particle interaction lengths are very. So the showers, I'm just showing a cartoon here on the right, they create a shower of particles, and that goes too long. So these detectors are a little bit larger as compared to the electromagnetic calorimeters. And then the muons, they just fly through, leaving just a track. So at the end, we also have to measure the position and momentum of the muons, the muon chambers. So usually we combine the information from the trackings and the muons. So the CMS experiment uses the state-of-art detector technology to identify and measure the kinematic properties. So that's the actual beasties, and this is sort of a technical marvel. So you can see here at the center, we have the pixel detectors, which are silicon based, because it's also the radiation hard and easy to make into the fine cells. So it's of the order of like 100 microns by 100 microns kind of scale. And after that is the electromagnetic calorimeter, where we have the showers, you can see the blue one. And then we have the Hadron Calorimeters, which is the scintillator and brass. So you can think of the 1 meter thick, the block of the brass sitting there. And then there are these gaseous detectors, what we call the muon chambers. Now the total weight of this detector is 12,000 tons, because there is so much of brass and also the magnetic solenoid, which creates the weight. And the overall diameter is 15 meters. So that gives you the scale that what we need. And the overall length, like the sideways, is like 21 meters. And we are using the 4 Tesla magnetic field. Actually, to be precise, it's more of 3.8 Tesla. And it has like sort of 1 million readout. So you can imagine that every 25 nanoseconds, we are reading out the 1 million events, 1 million channels. Okay, your mobile is just one chip in that sense. So you can compare these scale. So let's move on. And so what happens is the similar what I showed earlier, the simplistic picture. This is the more realistic picture, that the particles which are produced, they will leave their tracks if they are charged in the tracker. That's where you can see the tracks bending. If neutral particles, they will just go straight and they deposit the electromagnetic calorimeter and the Hadron Calorimeters, and the muons just fly through. And there is since it's a solenoid, the magnetic field direction change, and you can see the curvature changing. The weakly interacting particles, just a reminder, do not leave any signature in the detector. So how we are seeing this particle? So this is how the picture looks like if I see in sort of a simplistic way to sort of get a feel for what is happening in the detector, that at the vertex, the proton-proton collision is happening. And in the first picture, we are seeing the 4 muons coming out. And in the right one, I'm seeing the 2 jets coming out back to back. And there is a lot of tracks because there are a lot of charged particles coming out of these interactions. And these are really the enormous data rates, because we are talking about the 40 megahertz multiplied by the 1-2 milli, the megabytes every second. So we are really creating the data at the rate of 60 terabytes per second, and there is no way we can store it. So we are saving only interesting events. So out of this 40 the million events going per second, we are saving hardly 100 events. So our storage is essentially 1 kilohertz at the most. So we do a lot of real-time analysis. That is what we call the triggering system. I'm not going into details, but if any interest, I can come back to it later. And so we really do that within few microseconds. You need to know whether I want to save this event or not, whether I want to save this collision or not. By the way, I'm using the word collision and the events or collision events interchangeably. Now, next question is, how do we analyze more than billion collision events we collect every year? That's the sort of the 25 petabyte of the data. Okay. So what we want to do, we want to identify the collisions of the interest, that whatever PP collision happened, whether it is of my physics interest or not, or it has something more new to tell or not. It can be a standard model measurement, it can be new physics structures. As we said that all these heavy particles, they decay. Here I talk about the Z boson, which is like close to 91 GeV, which is, you can see that 91 times heavier than proton, roughly. This will decay to 2 muons. And what I see here are the 2 muons in the detector we measure. And these are really high momentum. Here I see the PT of like 800 GeV. Okay, so what do we do? If I say, okay, fine, I have 2 muons, what do I do with them? So you have to find out some kinematic properties where you can say, okay, it belongs to some particular category. A simplest example is check the invariant mass. And you all by now have done your special relativity, and you know that, okay, E square minus P square equals M square. And if these 2 muons are coming from the same mother particle, then they will really peak to, it will give the mass of that mother particle. So I can go over a lot of events. If these particles are not coming from same mother particle, there will be some distribution, some mass. Otherwise, it will peak at the mother particle mass. So here it should be the Z mass. So what we do is that I will show you an example. We take all the data, what we collected, where we have 2 muons, and what do you expect to see? Okay, so, and just make a frequency distribution, and this is the beauty of it. What you see here is all the events which we collected in one particular data set back in 2016. We take all the dimuons and just plot their invariant mass. So this is the frequency distribution of that. And you can see here that we have these distributions showing us the Z peak, which is the Z boson at 91 GeV. And these are all other known particles, the Jep psi or the eta or the omega or the phi. And you can see these peaks coming out in the various mass states, right? So this is one example of like how we find out the interesting collision events. Now, suppose I see 4 muons, then what do I do? Is it a Higgs boson, or it is just a ZZ production from the standard model? We do the same thing, that we try to find out, we look at their angular correlations, we look at their invariant mass distributions, we look at the invariant mass distribution of the 2 pairs, whether they are consistent with the 2 Z bosons or not, because Higgs is 125 GeV and the Z is 90 GeV. So Higgs cannot get into 2 on-shell Z bosons, right? One of them will be off-shell. So we can go over some of these kinematic distributions and see, and this is exactly how we actually reported the Higgs discovery. So you see here, the plot I'm showing here is the invariant mass distribution of these 4 lepton events. And you see here, the blue ones and the green ones was our known physics that comes from the standard model. But when we looked at the data, we saw something here, the red one, the red peak here, and we did not know how to explain it. And that's exactly where we figured out that, okay, fine, this is the Higgs boson we have been looking for, because this is consistent with what we are expecting. And then you go and measure all its properties, like its spin, its parity, it's the various interactions with the particles, and we established that this is the Higgs boson, the standard model Higgs boson. So by the way, when the Higgs boson was announced, I was actually at CERN, might not be in this audience. And that was really sort of, I mean, I could remember what I learned in my MSc days, and these equations materializing into the real particles. That's how I put it. So it was really an exciting day for me personally also. So I still remember the pages like the electroweak symmetry breaking taught by Rashmi ma'am only. So she's the one who introduced me to some of these physics. So the standard model is a remarkable, successful theory. But how do we do about the neutrinos and the dark matter? Okay, because this. So here again, we use a very simple concept, the momentum conservation. So the picture I show here is the 2 proton beams coming across, and that is the direction, what we call the beam direction. And what we are using here, and the direction other than that, perpendicular, that's what I'm calling the transverse direction. So You can think of that proton beam in z direction and the other is xy. So the initial protons don't have any transverse momentum, and the momentum conservation implies that the net transverse momentum of all the particles which is coming out of this collision should also be zero. Okay, that's the concept we use. So moving ahead, this can be illustrated in this nice picture that we have the two proton beams colliding. We have some event, some interaction happening. I have a lot of particles coming out, but if my visible particles don't sum up to zero, that means something has gone. Okay, and that is what I'm calling the missing transverse momentum. I sometimes use it ETMIS, sometimes PTMIS, sometimes MET. Here I'm using MET because it was easier to write on the slides. So if there is a non-zero missing momentum, then we say that something has happened and carried away the energy without showing any visible signature in the detector. Those can be neutrinos, those can be neutralinos from supersymmetry, those can be our dark matter candidates. So this magnitude of this PTMIS vector is what we have as a signature of these dark matter candidates. Okay. And here is an actual event where you see that everything, so this should be balanced in the transverse direction. This is transverse direction picture. You can see that every visible thing is going in one direction and there is a missing it in the other direction. Okay, and this is, we don't know whether it's the supersymmetry or a standard model neutrinos or a dark matter candidate. So even by event, we just cannot say. We have to do the statistical analysis and we go again, try to find out the kinematic distributions and try to see what has happened, whether it is a deviation from what we are expecting from a standard model or not. So what we have done, I mean, what I sort of explained to you so far was the invariant mass where the signature is coming from a single particle, from a same mother particle. But we can also see the similar way that we go and see the missingity transverse distribution and try to see whether we have any deviation from the standard model known physics or not. So the cartoon I show here is the same thing, that in the lower right plot is basically showing that, okay, there is a blue curve, which is some standard model going on. And there is this yellow one, orange one, which shows that, okay, fine, there's some new physics in the tails. The picture I show above is similar example, that if my data was consistent with the standard model or not, that's how what we try to infer whether there was some new physics going on or not. So I will explain that more in the next slide. So before we move to the actual statistical analysis of these events, what I would like to say here is there is a variety of such processes which can happen. The first one I'm showing is a sort of gluino-gluino production where the two supersymmetry particles are produced and they decay into a chain of particles, where in the end I might have some dark matter candidates, what I call the neutralinos here. These are the lightest supersymmetric particles. They will fly through the detector, giving me missingity. Or it can be the actual dark matter interaction production. But then I said, if only two dark matter candidates are produced, we can't see them. So we always need some visible tag. And that's what these photon or gluons coming out or the top quarks associated. We need these extra particles so that we have something visible in the detector to tag these particles. Okay. And these particles decay into a variety of channels. What we want to have is a good signal to noise separation. And that's why we look into the different finalistics. It can be a zero lepton, so that means there is no electron on muon in the event, or there can be one lepton, one electron muon, two electron muon, or a photon. Depending upon, we sort of categorize these events so that they are mutually exclusive, as well as give us a good separation. And moreover, they can give us different kinematic handles. Okay. And why I say so, that I will show in my next slide. For example, this one, the first one is essentially a simple, I sum up all the visible energy from these, or I can sum up all the invisible energy. So that's what my top plots show here. In this case, it is the visible energy and invisible energy. The field histograms are essentially what I expect from my standard model physics. And the dots show here, the black dots are the data. Okay. So if there was new physics, the data would have followed the blue curve, the field histograms plus the blue curve. But beyond certain point, it starts deviating with respect to blue curve. And basically we said that, okay, fine, there is no signature. My data is consistent with the standard model. So this was just looking at simple missingity spectrum. But then you can look at the single lepton events, and where you see here W decays to lepton and the neutrino. But then it gives one more handle, because this lepton and the missingity are coming from the same mother particle. So this will again have some angular structure as well as the mass structure. So if you look at the middle plot here, if I look at just count the number of events, you are trying to look for the 100 events in 10,000 events. Versus if I look at only the tails, it is 100 events in the 200 background. Okay, so this is how we try to optimize that how best we can look for our signal in this variety of ways. So there is a lot of creativity also involved here. The basic principle follows. You cannot really violate the momentum conservation or energy conservation. You cannot really violate the mass conservation. mass energy conservation, right? But then you can still be creative if you can come up with the new ideas and try to see that how I can make my signal well separated from the backgrounds. And now we also use a lot of machine learning techniques also in these kind of searches. Okay. So moving ahead, here I show the actual the papers we published. The left one is for a supersymmetry search, and this is done by one of my students who graduated 2 years ago. And here also again the data was consistent completely with the standard model, to our disappointment. But then okay, the standard model survives. And the right one is for a dark matter candidate associated produced in association with the top quarks. And here also the data nicely follows the standard model expectations. And we said that okay, fine, there is no new physics. Now, when I say this, what does it mean? As an experimentalist, my results are these, that I have the data observed, I have the background estimated along with the uncertainties. Along with the uncertainties is the most important thing. We take more than sometimes 2 years to establish one such plot, that this is my background estimation and this is my data. Okay, the uncertainties are important. Otherwise, you can easily claim a false discovery or lose a discovery. So both are important. Okay. So what we want to say here, that given these backgrounds, given this data, and given these uncertainties on the background, what is the maximum number of new physics which can be hidden in these uncertainties? That's how we are quoting our results. So suppose I say here gluino mass can be anything. Here the example which is shown in this the blue curves is of the order of 1.4 TeV or 1 TeV, but it can be any mass. So now the question is that what is the maximum signal which can be hidden in these uncertainties? And that's how we sort of our results we present. So the left figure I show here, on the x-axis is the supersymmetry mother particles, which is the electroweakinos, and the right, the y-axis is one of the daughter particles, which is also dark matter candidate. So here we see whatever the area covered under these curves is excluded. That means dark matter candidate with the neutralino second, the higher mass neutralino of a 1200 GeV doesn't exist in these particular scenarios. Okay, so as I said, that as an experimentalist, our results are essentially these background measurements, uncertainties, and the data. But to be able to talk to the our theory colleagues and put the physics in the bigger perspective, we try to make these sort of interpretations in the theoretical models. The left one here is for the supersymmetry, the right one is for the direct dark matter candidates. And here the dark matter candidates, we are talking about the masses of such particles which are the intermediary. And here also we see that, okay, we have probed sort of like few TeV particles and few TeV mediator particles. So far, the standard model survives, no luck with the new physics, but the quest continues. So there are many interesting results. And this is one example I'm showing. It's not possible to show you all these tables, and no point in showing you all these tables. But what we are trying to say here is that, as I said, that the W boson is 80 GeV, the Z boson is 90 GeV, and the Higgs boson is roughly 125 GeV. And we have probed up to 1.5 TeV particles in the electroweak production. Okay. And the strong production, we have gone further more. I think in strong production, we have probed up to like 2.2 TeV, 2.5 TeV. And more indirect one for the heavy bosons and things like that, we have probed up to like few TeVs. So a lot of interesting things going on. We still have a lot of data which is not yet sort of analyzed completely, and the quest still continues. So, but we do keep celebrating the success of the standard model. This is one of my favorite picture of the like sort of the measurements of the CMS. What I show here in the y-axis is the production cross section, so that at what rate these particles are being produced. On the x-axis are the different production modes. So the first bulk here, the first few columns are essentially W jets and the Z jets produced. And so far we used to give only one number for their production rate, but now we can give a large number of differential cross sections. The W plus 1 jet, W plus 2 jets here the quarks, basically W plus 1 quark, W plus 2 quarks, and how we go. And then there are the diboson productions. And then we talk about these triboson productions, so WWW, W gamma gamma, WZZ, those kind of production. And then we talk about the top and the Higgs. Now, the top and Higgs are quite interesting because they are probed to the dark matter searches also. They are now our tools also, as well as they do define how the electroweak symmetry breaking mechanism is. So measuring their properties, and if there is any deviation from the standard model physics, that can be another probe into the new physics searches and what is going on in the universe, which we don't know yet. So moving ahead, so what is next at the LHC? As I said that we are making a lot of searches. We have not seen anything new so far. In these particular searches, there are some deviations if you go for the intensity frontier, but which I have not covered. We still have too many unanswered questions: dark matter, supersymmetry, extra dimensions, what are the neutrino masses, the origin, the matter antisymmetry, Y3 generation of fermions. There can be, you can add many more, which are either the experimental observations or what is not aesthetically appealing to us from theoretical point of view. So right now, so this is more or less the timeline and the overall plan of the LHC. The arrow shows here that we are here, and we are already starting to prepare for the high luminosity LHC. So the LHC was shut down until now, and we are starting data taking, which what we will call the run 3 now. And that will continue for another 3-4 years. And then there will be a long shutdown, what we call LS3. And then we will really revamp the accelerator as well as detectors to be able to increase the intensity of our beams by of the order of 7 to 10 times. Okay, so these will be really, really sort of intense beams. And that's what we call the high luminosity LHC. Now, LHC started back in 2010, and until now we have corrected 1 FEM to 1 inverse, and next 3-4 years it will be another amount. So you can imagine whatever we collected in 15 years, 10 times more data we will collect in the 10 years. So you can imagine the challenges which are upcoming. So you can see here that the picture I showed you earlier, that there are 2 photons nicely, and you will have to find out such 2 photons in this mess. So that is what we are expecting at the HLLHC. So it is not only that we have to upgrade our detectors, algorithmically also there is a lot of creativity required and a lot of like challenges involved that makes it fun. That how do you find out your interesting 2 photons or 2 muons in this kind of mess? So one of my interests particularly have been to for the calorimeters. On the left, what I show here is the CMS detector and just a sketch of that. And the yellow piece I'm highlighting is the technology I worked on during my PhD. This is what we call the Hadron Calorimeter. This was the scintillator and brass technology. It's a calorimeter. As I said that you can imagine that why this is important, because you have to completely pack your detector that no particle passes through. Then only you can have your missingity measurement properly done. If you have the energy leaking out, you will confuse between the actual missing energy and what is the leaked out energy. So these detectors are extremely important for that purpose. So the yellow one I'm showing you here was the technology I worked on. And now we are working on replacing that one with the silicon-based detectors, silicon and the scintillators with the silicon photomultipliers. And that's what one of my students worked on. He recently graduated. This is what we call the high granularity calorimeter. The idea here is that what I show here, the hexagonal picture, you can see here, it is sort of like 11 centimeter one module. So I'm showing you here the 7 module, and that 11 centimeter will have something like either up to 200 channels, independent channels readout. So you can see what granular it is. It's a beautiful detector technologically. And this small piece then will have 60 million independent channels to be read out. Okay, so we have already preparing for this, and a lot of test beams and preparations going on at CERN, and even some labs set up the lab system test here in our labs also. So the picture I show above, the first one is one of my students working with the test beams, and that's the data we collected, and he graduated PhD for his PhD, and he is now joined one of the dark matter searches, the super CDMS, what we call. That's a direct dark matter detection. He actually started 2 months ago as a postdoc. So in summary, we don't know. It's all mystery. 95% of what we claim is only 4 to 5% that we say we understand, and it's still a lot to be understand there also. So there are a lot of new challenges, but there are many exciting times ahead. Okay, and if you don't believe me that, okay, this is all fiction or what I'm talking about is not the reality, no, it is reality, and this is the proof. So although I think I have been, so this is the picture from, I think 2 years ago. I think we met at the LSC tunnel. And although I have met Sudhir Ranewala sir more in the CERN and have more coffee and wine with him, but I think I don't have any picture with him. So this is the picture with Rashmi Ranewala ma'am and the host of the talk today. So thank you.
Very nice, Seema. It was really very nice to know what you are doing.
Thank you.
Why don't you leave a message for the young students of our department here where you were once there? The charm of physics, which is all what you are doing for the last 1 hour or whatever. Leave a message for them.
As I said, that explore. I think whatever it is, I mean, it's fun.
That's a very crisp message.
No, I'm serious about it because
No, it's true, but maybe Seema, you can expand a bit on, like whether we want to, sometimes you feel that coming from a small place, going there are no barriers in physics. Maybe you can expand on that.
And the glamour of observing nature.
Yes, it's basically, so, okay, let me, so there are two different questions. I think what you said and what Professor Vandana said. So the first thing is that I think the reason I got excited about the physics part was from the fact that we had the good lecture courses as well as the side-by-side the lab courses. Okay, and that's made a huge difference in my understanding and my excitement for the physics. Okay, when we were doing with I think it was taught by Professor Sada Singh, the quantum field theory to start with, and calculating all these electronic processes there, the QED basically, and go back and see the coincidence experiment or doing the Compton scattering experiment there. I mean, that was fabulous. You can read about what I think Professor Bhalla taught us and Professor Vinod Kumar also about this nuclear physics and all when we're reading the detectors. But going back and seeing the gamma ray spectrometer, I mean, that was the fabulous experiment. So there, I think now my students, I tease them that they don't do anything because they have this multi-channel analyzer and they get in one shot. What we had to do is really read those and calculate those graphs. Okay, so seeing the data is, I think that excited me like anything. That's simply beautiful. And the reason I enjoyed really the particle physics part, or in fact, now when I look back, any physics part, is that the interconnection between the theory and the crosstalk which happens, especially the way the atomic physics, nuclear physics, and the particle physics came about. I think that's super exciting. So, but now I think we get like sort of becomes an excuse that, okay, fine, there are labs which are limited. No, that point is correct. Even if you go for theory calculation, go and solve it. I still remember the double well potential calculations Sudhir sir made us do it during our second year BSc. He won't leave us without solving it. So doing it by once, although everything is available over Google and all the things, unless you do it yourself, it's not going to help out in long term. And the reason I said explore was essentially this only, because since Vandana, you asked me that, okay, fine, coming from the small places, I think I got lucky with one point is that my father was working with JK Tires and I got a good exposure in the sense that I saw people from all states right from the childhood. So they get sort of an acceptance for the variety we see around. But otherwise, I think we were limited in terms of the resources in other ways. The reason I said explore is that there is a lot of assumptions we make. The way I grew up was always in fear. ऐसा हो जाएगा, वैसा हो जाएगा. To the extent that I was afraid that, okay, whether I will be allowed to go for higher studies or not. Okay, financial problems are one thing. But even coming out of the sea, okay, fine, your cousins are getting in this way, your cousins are treated this way, they have given this optional life, not given this life. Get over those assumptions. As I said, your parents and your mentors and your friends are much more ambitious for you than yourself for yourself. I got lucky with that. So when I say explore, once explore, it's both your surroundings as well as the science. And the good part of physics is that you can do it.
Thank you, Seema. Just want to clarify. I don't mean small place in any bad way, because
no.
I grew up in a small place, and it is when you go to the big, you feel there is this. I mean, you get a complex, and you exactly have pointed out that don't make assumptions, don't get into the complex. You will find things better. Yeah. Thank you. I think I request somebody, either Rashmi or someone at the auditorium, to handle question answer. Yeah.
Before that, I have one comment to make here. When you say small places and the hesitations which come across and the complexes which come across, you are absolutely right in that. I think I have disappointed even Sudhir sir once very badly when he made me talk to Professor Archana Sharma from CERN, and I was like speechless. What do I say? So I completely agree with what you say, Vandana.
Yeah, so there are a few questions on YouTube, but I think we should first take questions from the hall, then we can go to the YouTube. So request somebody to take care of that.
So I'll ask the students if they want to ask something. Physics or non-physics, it's okay. I think they are just too odd right now.
Yeah. So let me read out the YouTube questions in the meantime.
Sure.
Yes. Please.
Okay. So there are a few on the YouTube. So one by Abhinav Chaudhary is, what is color glass condensate?
Color glass condensate.
I think this doesn't fall in.
That's yeah, that's
so,
more
yeah,
of
fine.
I mean,
material science
in
question.
case you want to give a pointer that where he should look up, it will be good. Otherwise, we can move on to the
plasma and color glass condensate.
Yeah.
Google quark
Yeah.
gluon plasma and color
Okay.
glass condensate.
There's another question: why we built LHC underground?
Why we build LSC underground? Because you need to have that much of space and away from all the, for example, the cosmic backgrounds and all that. So that helps to go a little bit underground and help. But I think it was also the logistics in the sense that where do you find such a place?
Yeah.
So without disrupting the environment.
Okay.
So it was, it goes through the lake and everything, right? All the train station goes above that. So it's a mixture of things.
Okay. So one more question: why we have so many detectors in LHC?
So many
Detectors
we have
in LHC.
Yeah, so I'm not sure if you are talking about the different experiments or the one detector only.
I guess in a given experiment, so many detectors is
Yeah,
my guess.
so yeah, so there are 2 points here. One is, so in a given detector, we have different detectors because the way particles interact with the material is the property of the particle as well as the material. Okay, so for example, here I can show an example of that. We have lead tungsten for the electromagnetic showers because it's compact, but that amount is not sufficient for measuring the hadron showers also. So if I use the lead tungsten only for the hadron showers, I will need something like 10 meters. Okay, and that's not possible. While when I'm using brass, 1.5 meters is fine to contain those showers, to contain those particles. Okay, so it all depends upon what is our sort of goal and what kind of particles we want to measure.
Okay.
Okay.
There's also some appreciation comments saying great presentation.
Thank you.
But there's one more question. Do CMS experiment gives us some idea about how gluons are organized inside the proton?
Yes, so we do measure the pattern distribution functions. There are several, so I think I showed only one small picture here. The one on the left here. So all these measurements, which is what we call the pattern density distributions, they do get updated because what we have from the previous experiments are at the lower energies. What we have from the deep elastic scattering and all the detailed ones. Then we have from the Tevatron, but then LHC is a completely different new regime of the energies, right? So we do constrain the uncertainties on them and the pattern distribution functions themselves. So that gives an idea that, okay, fine, how the gluons are distributed or what their momentum structure is.
Yeah. There's a question, can I explain CMS in easy way, like general terms? So can it be explained to the 12th class students?
So the name CMS is the, I did not intentionally specify that what does, and nobody asked me that what is the full form of CMS. So it's the compact muon solenoid, right? So what we want to do, as I said that, okay, these particles which are muons, okay, they just pass through because they are much heavier than the 100 times more heavier than the electrons. Okay, so they don't sort of give any radiations like giving out like the Bremsstrahlung. They don't undergo the strong interaction, so they leave a track. Now, if you want to measure these high momentum particles which are not really stopping in the detector, you want to have a really compact detector and with high magnetic field. Okay, so that's what the name compact muon solenoid comes from. Now, if I have to ask for the CMS, it's basically a set of detectors which has been organized in a way that we can really search for the new fundamental particles and the new interactions and study the standard model particles more precisely or interactions more precisely. That's what I can say.
Very, very nicely put, Seema, very concisely, and this one really great. I think now from the YouTube, we'll move back to your classroom in University of Rajasthan, Jaipur. Now I think students should have a little courage to speak up.
And questions from here for Seema?
Yeah.
I told you I was the same, so I can identify myself.
I don't think they are going to be asking much here.
Yeah, but
कुछ तो
please
पूछिए,
feel free
कुछ
to
तो
contact.
पूछिए, कुछ तो पूछिए कि उसको बम्बई जाके कैसे लगा, स्विट्जरलैंड जाके कैसे लगा, कुछ तो पूछिए. Because it's really a good opportunity for you to interact with her. We really, I mean, that's where I think even Professor Sudhir said that physics, non-physics, ask anything.
Nico, can I be heard? Can the students hear me?
Yes, you can.
बच्चा लोगों देखो, सीमा एक ही थी, एकाध और स्टूडेंट्स थे अपने यहाँ के जिनकी आंख में मुझे कुछ दिखता था. तो सीमा ने एक बात नहीं बताई और मैं अभी बता देता हूँ, यदि ये नाराज नहीं हो तो एमएससी करने के बाद इसकी इच्छा थी कि पढ़ाई वगैरह छोड़ दे. तो मुझे इसकी आंख में कुछ दिखता था, तो मैंने कहा बेटा थोड़े दिन जाके 1 साल रिसर्च कर ले टाटा इंस्टीट्यूट में, उसके बाद छोड़ देना पसंद नहीं आए. So I actually requested Seema to call her parents, and they were kind enough. While passing through someday, they stopped over in the university, and I requested them, Seema being the eldest child, I requested them कि भाई इसको 1 साल जाने दो टाटा इंस्टीट्यूट, उसके बाद आपको अच्छा नहीं लगे तो छोड़ देना, क्योंकि अपन लोग तो सब राजस्थान में रहने वाले हैं. राजस्थान में तो रिवाज यही है कि लड़की 22 साल की हो गई तो उसकी शादी कर दो बस, है ना. But Seema could cross all that. Similarly, there was another girl in the recent times, Lata.
Yes.
तो उसके लिए भी उसके पिताजी से भी मैंने बात की. उसका जर्मनी में फेलोशिप मिल गई थी, but her father did not let her go to Germany. वो बैंगलोर चली गई, but she did very well. इसके पहले बीच में 2 लड़कियां और थीं, उनके पिताजी को बुला के मैंने बात की, क्योंकि मुझे वो लड़कियां बहुत अच्छी लगती थी. लेकिन their father said nothing doing. ये तो स्कूल में पढ़ाएगी जाके, कहीं कोई रिसर्च नहीं करेगी. But so be it, such is life. तो आप लोगों से बच्चा लोगों रिक्वेस्ट एक ही है, चीजों को ध्यान से पढ़ो, अपने टीचर से खूब सवाल पूछो, which is what Seema used to do, है ना. And that is what used to make fun that is what used to feel great in classes. Chalo.
Actually, in the point which you brought in, I want to add, the TFR started this summer program for MSc first year students, women students, Vigyan Vidushi in 2020. And because of the pandemic, the program became online. And there was one, I mean, we all were disappointed because we thought, how would we really interact with the students? But what happened was, as a part of this program, there were lectures by eminent women scientists. And some of the students actually could make their parents and family members see those lectures to say that what is the future in science. And I think that's a great advantage, because I would like to emphasize it here that the support from the family is very important for pursuing the career. So to all the girls who are here, please also talk to your family members, and all the boys who are here, please make sure that your friends, your cousins will need support from you if they want to go further. And because, you have challenges, and when you want to go outside, if you want to fight with somebody or argue with somebody, it's much easier. It's very difficult to argue and fight with your family. So it takes much more internal effort. So I think the family support, it's well known that makes a lot of difference. And so it is, please, because many times people don't know what is a career in the research. So अभी ये जो opportunity है कि YouTube पे काफी लोगों के talks है, काफी career opportunities के talks है, आप आपके अपने फैमिली मेंबर्स के साथ भी बात करके ये ऑप्शंस भी उन्हें दिखा दीजिए, because they want best for you. They may be thinking in a certain way in which they are looking at that, so they also can be convinced. And जैसे सुधीर जी ने अभी बोला कि he could talk to some of the parents and explain to them what possibilities are. And so I think that's also part of the things which we would like to convey in this lecture. And one thing, since he talked about Seema going to TFR, I just reminded her. I think that when Seema came to give the TFR interview, I was in the committee, and she did really, really very well in the interview. Of course, that's why she was in TFR. But I'm saying that, so it is not that from Jaipur, the Bombay and TFR will look very far. But now when you look at people like Seema who have come from there and gone, next time, don't think that Pune, Bombay, CERN is all that far. The world has come very close now, and you can go places easily.
Yeah, actually, this was very, I think you reminded me of something which like things are so long forgotten now. So when I joined TFR also, it was not easy to start with. First of all, the Mumbai rains. You join in August and all you see is gray sky all the time. That was depressing. But on top of that, what happens is that all my batchmates, they were coming from, most of them came from the IITs or like some of these where they already had some research experience, right? So the situation was like, मुझे कभी 4 dimension पूरे नहीं समझ में आए. They never talked below 10 dimensions. They were all like theory aspirants. So at the end, I mean, you have to believe in that what you know. Okay, so when you go and talk to like work in Vandana's lab for one of the projects or one of the lab rotations, I think I knew my stuff. But then when it has to something else, of course, I could not speak in the coffee tables or the like late night chai discussions. Come over those things, they are no big deal. It's just a matter of getting the exposure and getting them sorted out. So you will all like sort of manage. And the family support is extremely important. But so is, as I said, that support is all around you. You have to look for it. But first, yourself have to be motivated that you want to do it.
Absolutely.
And there is one more, if I can make sort of, since I'm in a career stage and also the age group where it is like not juniors like the students sitting here and not as senior as my professors and my teachers here. So one of the things as girls, we also think like many of them I sort of sometimes fear about is that, okay, fine, we are doing PhD, aage kuch hona nahi hai. It will be like sort of coming from whatever. So there is some sort of a assumption in back of mind, knowingly or unknowingly. Get over that. Talk to yourself and you have to get over that. If you see that, okay, fine, there might be some break, fine, work hard now and cover up for that one. So all these things are doable. And Rashmi ma'am is actually the one sitting before you. She's a great example of that, who actually sort of made me observe the things that, I mean, when I came from, my mother was always a housewife. She had her own realm of things, but that seeing a working woman was not like sort of an obvious thing for me that how people manage. Right? So get over these hesitations. The world has changed a lot now, at least what it was when I was growing up.
And if you take a step, you will find a helping.
You will find out way. That's
so, but you need to take a step, because unless you take a step, nobody will realize that you need a helping.
And by the way, so one of the reasons I mentioned, sorry, going back to some work stuff, that one of the reasons I mentioned all these experiments and all, I am not at all expert. The reason I mentioned is there are a lot going on across the world. So it's not that LHC is the only end of the world or the astronomy is only end of the world or whatever happens in India or because your friend went somewhere. All the information is available. And the dark matter experiments, there are some 50 of them going on right now also. So, and the other point, which I think I made a mistake of not including one slide, which I sort of recalled a bit later, is that a lot of these also have societal applications. So even if you're doing well in the nuclear physics and all, there is a lot of research opportunities in the medical applications and the industry applications. So if I tell my students that any of them can go to the medical applications, I will be proud of them. So there is a lot to explore. So it's not just like limited to only research in particle physics.
I would only like to add and also emphasize for the students that the coming years with the high luminosity LHC and the FCC in future is going to be one of the most exciting times for the high energy physics and experimental high energy physics. And the students of today are the ones who are going to be working there.
Exactly.
So we really want you people to come up, to step up and take up the necessary responsibility of taking up the research further.
Yes, I'm sure many of them will go to discover the physics beyond standard model, more physics.
We have a student who wants to ask a question.
Yes, please.
My question is that is there any energy valuing for?
Yeah, Acha.
Hello, ma'am.
Hi.
Thank you for your wonderful lecture. My question is that is there any energy barrier for particle when we accelerate the particle? Is there any energy barrier when we are not able to understand what type of interaction is happening? So is there anything? Something is there?
I'm not sure. The energy barrier, you mean what is the maximum acceleration we can provide to particle, or is something else?
Is there any energy barriers? जैसे बोलते हैं कि 10 to the power 19 या फिर 9 मेगा इलेक्ट्रॉन वोल्ट
Yes.
is
So we are limited by the accelerator technology, right?
yes, ma'am.
But you have the 27-kilometer ring. You can keep accelerating particle, but we have to maintain in the same ring, right? So right now we are using in the LHC. So this ring right now we are using, for example, it's the 8 Tesla magnets, the big magnets, right? So if you can increase the this magnet technology, you can improve that. In the same ring, 27-kilometer, we can have more energy particles, more acceleration.
My question is that कि हम ऐसा होता है कि हम जो इंटरेक्शन है अपने वहां पे हो रहा है वो हम पता नहीं कर पाते कि कौन सा इंटरेक्शन हो रहा है एक्चुअली
तो दैट इज वही हम लोग का काम है ना लाइक अवेल हम कोशिश कर रहे हैं जानने की दैट व्हाट कैन बी द न्यू फिजिक्स सर्चेस व्हेन आई से सिर्फ पार्टिकल्स नहीं है न्यू इंटरेक्शंस भी हो सकते हैं पर अभी तक ऐसा कुछ मिला नहीं है
कि अब तक जितने भी एक्सपेरिमेंट हुए हमको एग्जैक्टली पता होता है कि कौन सा इंटरेक्शन हुआ है या फिर ऐसी एनर्जी लेवल है कि इस एनर्जी से अगर एक्सेलरेट करे तो हमको पता ही नहीं चलेगा कि ऐसा कभी इंटरेक्शन कौन सा होता है
सो अब तक जो हम कर रहे हैं सो बेसिकली व्हाट वी आर डूइंग इज दैट वी आर रियली द प्रोटॉन्स एंड द क्वार्क इंटरेक्शंस वी आर टॉकिंग अबाउट दोस आर ऑल स्टैंडर्ड मॉडल पार्टिकल्स दैट इज वेल अंडरस्टूड फिजिक्स राइट सो इसी एक्सपेरिमेंट में कुछ नया हुआ था राइट व्हेन द हिग्स पार्टिकल वाज डिस्कवर्ड तो जो नई बात कर रहे हैं ना आपकी जो समझ में नहीं आया है उसका हम वेट कर रहे हैं डेस्परेटली जब भी आएगा सबसे ज्यादा एक्साइटमेंट हमें होगा
थैंक यू सो मच थैंक यू
या सो दैट्स द क्वेस्ट फॉर गुड
Okay, Seema, then we can wrap it up now.
Okay, thank you so
Vandana,
much.
are there any more YouTube videos, YouTube questions?
No, I think we can wrap up there. It was a wonderful talk and very nice. And thank you all. Thank you, Seema, and thank you, University of Rajasthan for hosting it.
Yeah, please feel free to contact anytime. I mean, any of the students, and I'm more than happy to come back if there is anything specific or want to elaborate on anything.
When you say come back means you're planning to come to Jaipur, Seema?
No, I meant the talk. It can be online or it can be Jaipur. Abhi to koi plan nahi hai.
Chalo. Okay.
But I will meet you when I come to Jaipur.
So much for organizing it. Much appreciated. And we really appreciate that you thought of Rajasthan University while organizing this IPA colloquium. Thank you so much, Vandana.
Thank you.